Hello, everyone. I'm Eric Hyam, Technical Editor with Microwave Journal, and I'd like to welcome you to this webinar entitled Antenna Material Solutions Across the Electromagnetic Spectrum, sponsored by Rogers Corporation. We have two presenters from Rogers for today's presentation, John Coonrod, Technical Marketing Manager, and John Ekus, Market Segment Director for Aerospace and Defense, and they're both from Rogers Corporation. Increasing system bandwidth and higher frequencies in new wireless applications is increasing the importance of optimized antenna designs. This webinar will review the broad antenna solutions across the electromagnetic spectrum, and we'll look at basic RF antenna concepts on PCBs and how material selection and PCB fabrication techniques influence antenna performance, along with an overview of a few studies and supporting data that illustrate these topics. But before we begin that, let me cover a few logistics. If you'd like to download the presentation slides for reference, you'll find a copy in the handouts window. We'll have time for questions after the presentation. To ask one, please type it into the Q&A window at any time. And the presentation is being recorded, so it will be available to watch again and recommend to your colleagues. Now, let me introduce our speakers. John Coonrod is the Technical Marketing Manager for Rogers Corporation's Advanced Electronics Solutions. John has 34 years of experience in the printed circuit board industry, with about half of this time spent in the flexible printed circuit board industry, addressing circuit design, applications, processing, and materials engineering. For the past 20 years, he has been supporting circuit fabrication, providing application support, and conducting electrical characterization studies in high-frequency circuit materials. John is the chair for the IPC D24C High-Frequency Test Methods Task Group, and he holds a Bachelor of Science in Electrical Engineering from Arizona State University. John Ekus has over 35 years of experience in electronic materials and RF components and subsystems, including more than 15 years directly in support of defense electronics. John's career began in process engineering and R&D, specializing in multi-layer electronic ceramics before transitioning into business development and market-facing roles. He is currently the Market Segment Director for Aerospace and Defense at Rogers Corporation, where he is working on positioning the advanced material technologies Rogers is developing into key aerospace and defense programs. So with that, over to you, gentlemen.
Thank you very much, Eric. We appreciate the introduction, and to everybody online, we appreciate you guys attending our webinar today. I'm just going to take a very few brief moments to talk about Rogers for those of you who may or may not know about Rogers. I scrolls here a little bit, and then I'm going to turn the presentation over to John Coonrod, who's going to take you through a heavy load of the technical content that we want to present today. For those of you who don't really understand Rogers or don't really know Rogers that well, we are a global leader in engineered materials, and I like to focus on engineered materials. Many of you will think of us as a copper-clad laminate supplier, feeding the printed circuit board industry, which is significantly a large part of our business today. However, we do develop a lot of engineered materials to help enable, especially in our market, the aerospace and defense market segment. We're a multinational corporation with headquarters in Chandler, Arizona, and we have been around for over 187 years, where we've been adapting and anticipating the changes of the market segments and trying to develop those materials and get those out into the market as fast as possible to enable your technology advancements. As I mentioned, we are one of the oldest public companies in the United States or in America. We were founded in 1832 and have our legacy in the aerospace and defense world going way back to some of the early satellite applications with NASA, which is where the genesis of a lot of our aerospace and defense material systems had sent. Today, we are recognized leader as a high reliability, high performance material solution, serving and enabling a number of the world's defense electronic systems. You could see us as high circuit materials, radar, comms, nav, space, satellite, and several advanced materials technologies, 3D printable, very low loss dielectric resins, formed shaped dielectrics for 3D structures, RF transparent windows, lenses, and radiating elements. I'm going to now pass over to John Coonrod and allow him to dig into antenna material solutions across the electromagnetic spectrum.
Okay, thank you, John. And I'm going to back up a couple of slides and run through the agenda real quick. It's probably not that important, but I just want to make sure everyone knows what we're going to be getting into. John's already gone through the quick move through Rogers' history and who we are. And after that, I'm going to talk about some basic concepts for PCBs, just making sure we're all on the same page. And then talk about some critical material properties that relate to antennas, and then some circuit fabrication issues that we've dealt with over the years and wanted to share some of our learning experience. And then finally, we'll give a little bit of information on some studies that we've done over the last couple of years on antennas. So to begin with, I was going to start off with explaining some terms again to make sure we're all on the same page. And I'm going to be talking about PCBs or circuits. So normally when I say PCB, I'm referring to the circuit itself, or it could be PWB. That's another term for the same thing, printed wiring board. My term when I use RF is really more of a generic term, so it's anything that's not DC. Microwave, usually when I say that, I really mean it's a range of frequency from about 300 megahertz to 30 gigahertz. A millimeter wave, I'll be referring to applications 30 gigahertz to 300 gigahertz. Dielectric constant, I use the term decay, which I really don't think is the best term, but that's kind of the habit I've got into, and our industry kind of goes that way as well. Anyway, decay is relative permittivity, or epsilon sub r, or E sub r sometimes. And then DF is what I'm going to refer to for dissipation factor, which is related to tan delta or loss tangent, and that's some of the quick terms I'll use. The next few slides are things that I've talked about many times in our presentations, and it's really just to make sure, again, that we're all, all understand the same thing. So to begin with, I want to talk about insertion loss, and this is a simple definition for insertion loss where it's made up of 4 different components: conductor loss, dielectric loss, radiation loss, and leakage. And normally I spend most of my time talking about conductor loss and dielectric loss because radiation loss is really, it's rather difficult to get your arms around. And I am going to talk about that a little bit more today, but I can't really do the subject much justice in this time frame. But anyway, I'll give a quick introduction to radiation losses, things like that, because it does relate to antennas. And then the leakage loss topic, I'm really not going to talk about today. That normally is not an issue in our industry with our materials. There are some exceptions, but again, I'm really not going to touch on that one today. So this is also something I've shared many times. I think it's a good visual way to think about how these different components of insertion loss interact with the actual loss of the circuit itself. And to start with the middle chart, which has the legend, that's a 10 mil thick circuit being tested for insertion loss on the y-axis in dB per inch, and x-axis is frequency going to about 20 gigahertz. The thick purple curve is the measured insertion loss using a differential length method. And the blue curve and the red curve are models of the amount of dielectric loss and conductor loss respectively, which add up to be the green curve, the total insertion loss. And the insertion loss, you can see, is pretty closely matched to the measured loss, so that's a good sign. And it's probably good enough for the example I'm showing today. But what would be interesting is on the next slide, when I add in radiation losses, you find that simulation is actually a little bit closer to the actual measured results on the 10 mil circuit that I'm showing here, and actually the 30 mil thick circuit, which is to the right. But anyway, back on this slide, what this is really showing is for the middle chart that there's more conductor losses, red curve, than there is dielectric losses, blue curve, that make up the overall insertion loss. And if you go to a thinner substrate using everything the same materials, same everything, except maintaining the 50 ohms, which means you have to get a more narrow conductor on a thinner substrate, then what you get is more conductor losses. The red curve increases, the overall insertion loss increases, And a lot of that's due to a more narrow conductor causing more conductor losses. Basically, you have less conductor to support the RF energy. And then on the right side, far right, that's the other end of the spectrum with a microstrip transmission line on a thick substrate, 30 mils thick. And here you can see the red curve, the conductor losses. That's not the dominant component now. It's actually the blue curve, dielectric losses. So in this case, if you had an application that was using a 30 mil thick circuit and you wanted to improve the losses, the thing to think about would be going after changing the blue curve, the dielectric losses. And you can do that by just changing materials that have different dissipation factor, using a lower loss material. Or you can also do that with smoother copper, but the smoother copper affects the conductor losses, and for a thicker laminate, the conductor losses are not really the dominant issue usually. That's the thinner laminate. And when you go to higher frequencies, like a lot of our millimeter wave applications now, you'll see that they do use a thin laminate, and that's for many different reasons. But one thing that is obvious with a thin laminate is that the conductor losses dominate much more, and that's really intuitively just because the copper planes are now much closer together, so the roughness of the copper is going to impact the insertion loss and the phase response more significantly on a thin circuit. And one way to improve the losses then in that case is conductor related, so it would be using a smoother copper if you could, or maybe even a different plated finish. The metal plated finish that's applied over copper also affects the conductor losses, and it will affect it more on a thinner circuit than it will a thicker circuit. The next slide is actually similar to the one I just showed, but now I added in radiation losses into the model. Now this model, by the way, is based on closed form equations, so it's not as accurate as field solving, but it is good for illustrating the points here, I think. So on the left chart here, I'm showing the 10 mil thick transmission line that I showed on the previous slide. Previous slide was the middle chart with 0.7 dB per inch loss at 20 gigahertz. And right now you can see that's adjusted a little bit from the last slide for the model, and I'll step back so you can see that. On the model on the last slide, the green curve hit about 0.65 or so dB per inch, and now with radiation losses added, it's about 0.7, so it's just about right on the money compared to the measured results. So the radiation loss makes a little bit of difference with a thinner substrate, but a thicker substrate, shown to the right here, 30 mil thick, here you can see the radiation losses are much more significant, and the radiation losses are the purple curve. And at lower frequency, the radiation losses really don't add much, but as you get higher in frequency on a thicker substrate, the radiation losses become much more significant, and this will make a pretty big difference in insertion loss, but it also can make differences in phase response and a few other things. So just looking through some relationships for radiation loss, here's a quick comparison, and basically as the frequency increases, you will get more radiation loss. That's the normal response. And also as the circuit substrate changes, if you go from thin to thick, a thicker circuit or a circuit using a thicker substrate will have more radiation loss. And then dielectric constant, low dielectric constant is going to have increased radiation loss. Higher dielectric constant will have lower radiation loss. And then for circuit issues, the circuit design itself can support or not more radiation or more radiation loss. And in the case of microstrip, it is a dispersive transmission line, of course, but it does radiate, and it will radiate as you get to higher frequencies. That's just kind of natural. Grounded coplanar waveguide can radiate, and you can do the design such to where you can minimize the radiation, or in some cases maybe eliminate it altogether. And then strip line is probably the best when it comes to radiation or not radiating, and it's an enclosed system, so to speak, so you really don't get radiation out of strip line, assuming that all the design is done correctly. Also along with radiation is signal launch, and that is the transition of the connector to the circuit. So any place you have a impedance mismatch or any kind of a transition, you can get some radiation in that area. So that's one thing to consider. Usually signal launch or that transition is more problematic as you go to higher frequencies. And same with the next bullets, the spurious wave mode propagation and unwanted resonances. Those actually can cause some radiation too. And then impedance transition discontinuities, like I already said, that can cause some radiation as well. So just to explain the radiation a little bit more, I thought I'd go through a couple of slides of some basic transmission line concepts. And this one's showing a system that is mismatched. And what it is a very simple system between a generator generating some RF power and a load using that power to do some kind of work. Transmission line connected together. If the transmission line was 50 ohms and the transitions were 50 ohms and the input and output of these devices are 50 ohms, you'd have a matched system and you would have a very efficient transfer of energy from the generator to the load directly. Whenever you get any kind of impedance mismatch, what you get is a reflection at that mismatch point, and between the generator and the transmission line going from 50 ohms down to 30 ohms, that's going to cause a reflection, and reflected energy will go right back into the generator, which is generally not a good thing. And then as you move down the transmission line a little more, you'll see there's another impedance transition there going from 30 to 50 at the load, and that's going to be another reflection point. And actually, you can get these reflection points that would actually go back and forth on here as well. But the bottom line is these reflections can be problematic. They will cause decreased or worsening return loss. And basically, the load is not going to get the energy that it's been designed to receive. Now, how that applies to an antenna, I'm showing an antenna on, or a very simple antenna system on top and bottom of this slide. On the top is a system that just, I would say, as is. So you have a radiating element connected to some kind of transmitter. And in this case, the radiating element is going to be a very low impedance, and that's pretty true for the patch designs that are used as radiators in Microstrip. They're generally a very low impedance, and that transition from the 50 ohm feed line bringing the energy from the transmitter to the antenna elements, that transition from 50 ohms down to a very low impedance causes a lot of reflections, so naturally a lot of energy gets reflected back to the transmitter, and that means the energy going from the transmitter to the antenna, a lot of that energy is not getting to the radiating elements, so the antennas, this overall system, the antenna is not going to be very efficient. Now, if you look at the bottom portion of the slide, this is when an impedance matching network was applied between the feed line and the radiating elements, and that impedance matching network does, as the name implies, it's going to match the impedance between the feed line and the radiating elements. And when that's done, you minimize the reflections and the return loss improves, and you get much more energy to the radiating elements than you would without the impedance matching network. And one thing I'd say about the impedance matching network is that's really pretty critical. As you get to higher frequencies, it's more critical, and also consistency for materials, for dielectric constant and other properties, that can affect that impedance matching network probably more so than the radiating elements. So when there are decay changes due to temperature or other things, a lot of times the radiating elements are affected. Well, they're always affected somewhat. It depends on the design. But the impedance matching networks, since they're frequency dependent and things can shift with a shift in decay and stuff like that, that's usually where the problems pop up at normally. It depends on the design, of course. So here's a simple definition of a microstrip patch, and these formulas are approximate, but it does give you kind of an idea of what's going on here, that along the length axis, you get the resonance, you might say, and you can also put this in an array form to where you can have many different of these patches that will radiate a pattern individually, and when blended together correctly, you might say, in design, you can form the radiation pattern that is desired. Let's see. So there's different ways to use feed lines to bring energy to the patch itself, and there's also different ways to couple to it. And here's a few different examples of coupling a feed line to a radiating patch. And each one of these have their own trade-offs and benefits and limits and things like that. But again, at lower frequencies, these transitions and connections and impedance matching and things like that, that's typically easier than when you go to higher frequency. And I'll explain some of the frequency differences as we move along here. So here's showing the radiating patch once again, and in this case I'm showing a quarter wavelength impedance transform between the feed line and the patch, and that's to again ensure the maximum amount of energy is being transferred to the patch and less energy is being reflected back. The arrows that I've shown here is just simple field lines. I'm trying to give a visual idea of what this looks like, because later as we talk about circuit fabrication issues and how circuit fabrication can impact antenna performance, understanding how the fields look will help you understand why these different concerns do have an impact on the antenna performance. So an ideal material for a microstrip patch antenna would be with the properties listed here, with the exception of the bullet at the very bottom is a typo where it says low thermal conductivity. That should be high thermal conductivity. My apologies. But anyway, for ideal material for a microstrip patch antenna, some of the ideal properties you'd want is using a thick substrate for one, because looking through the radiation losses and the relationships, a thick substrate will cause more radiation, and that's actually what you want from a radiating patch for an antenna, obviously. So a thicker substrate could be used. Lower decay also causes more radiation. Low profile copper is something that's usually considered as you go higher in frequency, but it can be beneficial at low frequency. The low profile copper I'm talking about is the copper cladding at the interface of the substrate copper of the laminate. If it was a microstrip circuit where you have signal on top, ground plane on the bottom, that interface between the substrate and the copper, those interfaces, that's the surface roughness or the profile that I'm talking about. And when that's roughened, that will cause different effects on the feed line and the patch. But the effects are generally degradation. So rougher copper usually has increased insertion loss, and it can shift the phase angle as well. Low TCDK, that's important to understand as well. With some applications, other applications, it may not be as interesting, but low TCDK, thermal coefficient of dielectric constant, that is basically saying if you have a material that has a low TCDK, that's saying that the dielectric constant of the material will not change with temperature significantly. And I'm going to talk more about that because I've seen that come up multiple times in troubleshooting different issues with antennas. Low moisture absorption, anyone that's worked in the industry for some amount of time realizes that's a pretty big deal, that moisture, if the circuit material is high in moisture absorption, it can absorb humidity from the environment, and as the humidity changes, so would the amount of moisture in the substrate, and the water vapor or moisture in the substrate is a very high dielectric constant, and it's polar and causes a lot more losses. So the moisture absorption is really a consistency issue, and having a low moisture absorption substrate is very much desired. And then finally, the bottom bullet that has the typo, again, my apologies, instead of low thermal conductivity, it should be high thermal conductivity for applications where you have higher power levels. And some of these applications with higher power levels are microstrip patch arrays, where each individual radiating element may not see that much power, but the power coming in from the feed line before it's divided off into the array, that could be a significant amount of power. And sometimes there is some heating due to that and some thermal management issues. And in that case, using a material with high thermal conductivity would be desired. So that's kind of a list of the ideal material properties for antennas. And here's some information on antennas operating at lower frequency. And that's all relative, I guess. To me, lower frequency is the lower microwave range, around 300 megahertz up to probably 6 or 10 gigahertz or so. But anyway, with these lower frequency antenna applications, it's desired to use a thicker substrate. There's a lot of benefits to that, to the antenna performance. But some of the things you should think about is with a thicker substrate and having improved radiation at the patch, that also means that the feed lines bringing the energy to the patch could radiate too, and with radiation on the feed lines, that's actually going to reduce the amount of energy that gets to the patch, the radiating patch. So you don't want the feed lines to radiate. So that's kind of the juggling act sometimes in the case of a lower frequency antenna using a thick substrate. that you need to get good radiation characteristics of the patch, but you don't want the feed line bringing the energy to the patch to radiate. And I'll talk about that a little bit more as we go along. Spurious wave modes can happen on a thicker substrate at lower frequencies, even though spurious modes are usually thought of as higher frequency, but it can happen at lower frequencies as well, so that's something to keep in mind. And unwanted resonances, that certainly can happen, and probably the most common problem I see along those lines is the relationship between the feed line and the substrate thickness. And what I mean by that for a microstrip, the distance between the signal plane and the ground plane, that's the dielectric thickness. When that's a big thickness, or let's put it this way, if that thickness happens to be 1/2 wavelength of the operating frequency, you will establish a good resonance between the signal plane and the ground plane, and that resonance will disturb what the desired outcome is for the design of the circuit. So that resonance is unwanted. That's something else that needs to be kept in mind. And then also the lower frequencies, just by the nature of having long wavelengths, the patch sizes are going to be bigger and the antennas overall are going to be larger. And one way you can help this large format is by using higher dielectric constant material. So higher dielectric constant material will shrink the footprint, you might say, because higher dielectric constant material causes a smaller wavelength, and the patch size is based on wavelength. The drawback with higher decay materials is it will cause less radiation. So if you remember back about that slide I showed with radiation relationships, one of them is dielectric constant. A low dielectric constant is good for radiation, high dielectric constant bad for radiation. So that's another thing to keep in mind. And then finally, a thicker substrate or a circuit built on a thicker substrate will can have more issues with thermal management, because now the heat flow path from the signal plane through the material down to the ground plane, that heat flow path is longer, where the ground plane is usually connected to a heat sink or something like that for cooling. But anyway, for a thicker substrate, that heat flow path is going to be longer, and that's usually more problematic for thermal management. So in that case, having materials with high thermal conductivity would be desired. List of materials shown here are materials that are commonly used at lower frequencies, and the only ones I didn't show in here, and I probably should have, was some of our higher thermal conductivity materials. Even though most of these are in the range that have high thermal conductivity, the TC parameter on the far right column is thermal conductivity. And normally we think of thermal conductivity in the range of 0.5 or greater is considered pretty good for the dielectrics used in our industry. So most of these are actually in a pretty good state or have pretty good properties for thermal conductivity. But we do have materials like the TC350 Plus that are much higher, 1.27 watt per meter K. And then also the RT Duroid 6035 HTC, that's 1.44 thermal conductivity, 1.44 watt per meter K. So we do have materials that are helpful for thermal conductivity and thermal management issues. This slide is bringing up an interesting point, I think, and that is at lower frequencies and having a form factor that's much bigger, of course, there's not too many ways you can really shrink that down without juggling the radiation effects with the patch and other things. But there is one neat trick that I like, and this is a material that we brought to market a few years ago called Magtrex. And as far as I know, this is a pretty unique material. It is a magnetodielectric material, and basically what we did was we formulated a material that would match the relative permittivity, dk, to the analog of that for magnetic properties, mu sub r. So mu sub r is the property in magnetics that affect a magnetic field, and dk is affecting electric fields. Simple way to think about it anyway. So when those two numbers are the same, that causes a lot of good things to happen actually for antennas and actually for miniaturization. So you can see the formula down to the bottom left. That's showing what happens when the dk and the mu sub r are about the same value. Then you can actually miniaturize the antenna significantly because the lambda, in this case wavelength, is decreased significantly. And then to the right of that is what happens with the substrate impedance itself. And what we are doing here is if mu sub r and epsilon sub r are the same value or very near the same value, that one component goes away. And now you have a substrate that's got the impedance of free space, basically. And that's a really good thing for radiation and transitions between the radiation plane and free space. Now moving on to higher frequency applications for antennas. We've worked with these applications over the years many times, same with the low frequency applications, of course. But when you get to higher frequencies, you have more things to worry about generally. And at higher frequencies, usually thinner laminates are used because the thinner laminates will help deal with some of the issues that you've got to worry about at these higher frequencies. So one thing I'll talk about that you need to be concerned about when using the thinner laminates is the copper surface roughness, which I already talked about a little bit, but again, that's the surface at the substrate copper interface of a microstrip. And that interface, if the copper is roughened, that will have an effect on insertion loss. A rougher copper will have more insertion loss. A rougher copper also will cause an increase in phase angle. It will slow the phase velocity, and it will affect propagation delay. So there's several things that copper does, and when it's in a thin format, so when the circuit's using a thin substrate, the copper planes are close together, and that means the effects of the copper are going to be more exaggerated. And in the case of antennas at higher frequency, usually it is using, the antennas are using thinner substrate. And the thinner substrates to actually help deal with some of the non-desired radiation of the feed lines and a few other things. So at these higher frequencies with a thinner substrate, a lot of times the RF designer will go from a microstrip feed line to a grounded coplanar waveguide to help deal with some of these things they don't want, unwanted modes and resonances that's not desired, and radiation on the feed line, all that stuff. So if the grounded coplanar waveguide is designed correctly, it can address those issues. My only concern there, and my big concern there, is what I've troubleshooted over the years with millimeter wave using grounded coplanar waveguide is grounded coplanar waveguide is much more impacted, I should say the RF performance of grounded coplanar waveguide is much more impacted by circuit fabrication issues than is microstrip and probably even strip line. So that's something to keep in mind, and I'll talk about some of those issues as we move along in the presentation. And then one of the tricks that's used, and I've seen done several times successfully, is on the outer layers of a multi-layer circuit to have a thicker RF material, and then on the inner layers have thinner materials. So the outer layers that's going to have the radiating patches gets the benefit of the thicker material. However, if you put the feed line on the inner layers, something like a strip line possibly, now the strip line feed line is not concerned with radiation because strip line is so good for not having radiation. So you can bring energy to the array with very little radiation, and you can control the modes and different things like that. Now the trick is transitioning from that strip line layer, inner layer, up to the patch. And at high frequencies, that can be difficult to deal with. It's very doable, but the RF designer really needs to spend a little bit of time, a lot of time actually, making sure that transition is clean and that the circuit fabrication variables will be accounted for as well. Now, a lot of the materials that are used in these millimeter wave applications shown here, specifically for 77 gigahertz automotive radar, the RL3003 is the material that's been used most in the industry. The RL3003G2 is actually the optimized version of that material, optimized for millimeter wave applications. And then the 4830, the CLT-MW, and the Speedwave 300P, those materials are typically used in applications where you have a multi-layer RF structure. So in some of these millimeter wave radars, what you have is at the top level, the microstrip portion of it, signal on top, ground plane on the bottom, or in this case, ground plane on layer 2 of the copper. That is going to be probably the RL3003 or the 3003G2, and then below that would be different materials. It could be cheaper materials like FR4 for ground planes, power planes, data lines, different things like that. But on some of the later radars now, that is an all RF package. In other words, the multilayer is using all RF materials, and these radars are typically very high resolution radars that have a lot more things going on with them, basically. And in that case, that's when you want to use something like a CLTMW or the 4830 for the core material, and the the Speedwave 300P prepreg for the bonding material. And the reasoning behind that is those materials are a little bit easier for fabrication because they do have glass reinforcement. The glass is spread glass, so you don't have to worry about the glass weave effect. But they are a little bit easier to deal with because the 3003 and the 3003 G2 are not glass reinforced, and they're very soft materials. Now, these materials have been used and are still used in very high volume right now, so it most certainly can be done. But for better yields and things like that, typically the glass reinforced materials, 4830, CLTMW, and Speedwave 300P are used. So some of the things to think about for circuit fabrication and how it can impact antenna performance. And to begin with, I wanted to show some basic illustrations of field lines. And once you understand how the field lines are of the circuit, it's a little bit easier to understand how the circuit fabrication process can have an impact on RF performance. So on the left is a view of a microstrip, and bottom left is a cross-sectional view. The orange is the conductor, red is current density, blue lines are the electric fields. To the right is grounded coplanar waveguide, and you can see that there are electric fields between the ground signal ground on the top copper layer, and there's also electric fields between the signal plane and the bottom ground plane. And one thing that comes into play a lot with antenna performance is the final plated finish. That does most certainly have an impact on the conductor losses, and whenever it's a thin substrate like millimeter wave, then that's going to be a pretty big impact, because a thinner substrate, when the copper planes are close together, the conductor effects are exaggerated. So applying a lossy finish to this circuit will be, you will see a difference in losses and even phase response. And the reason why a microstrip is a little funny, because if you look at that, most of the fields are between the signal plane and the ground plane, and when you apply a plated finish to the exposed signal conductor on top, it really can't get at that interface between the signal plane and the ground plane, or shouldn't anyway. But it does affect the left and right corners, or left and right edges of that signal conductor, where there is higher current density and more fields. And that's the edge effect, you might say, of the lossy plated finish when applied to the structure. However, in the case of grounded coplanar waveguide to the right, that same concept where you have fields interacting with a plated finish, in this case you have ground signal ground, and you basically have four sidewalls that have a lossy finish on it with coupling fields going through them. So now you have four layers of that lossy finish that's coming into play. And that can be substantial. And if you do a comparison between microstrip on the left, grounded coplanar waveguide on the right, actually using the same material, it's 5 mil thick RO3003 with rolled copper. And on the left, the microstrip, you can see between the bare copper curve gray and the ENIG blue and orange curve, that is ENIG with thin nickel, ENIG with thick nickel. You can see there's a pretty good difference in insertion loss, and there is a difference in insertion loss between the thin and thick nickel. Now what happened here was I asked the circuit fabricator to build circuits for me, bare copper and also circuits with ENIG, electrous nickel immersion gold, having nickel on the low side of the normal specification for how much it can vary, and then nickel on the high side for how much it can vary. And that's what you're really looking at here, is the variation that can happen when using ENIG and how that affects RF performance for insertion loss. And on the right, the grounded coplanar waveguide, which has these fields coupled through several layers of this finish, ENIG in this case, you can see that the effects between the bare copper and the ENIG thin nickel and thick nickel are exaggerated over the microstrip, or more, more aggressive anyway, however you want to look at that. So if you are using a grounded coplanar waveguide, you need to keep in mind that it's going to be more sensitive to this plating finish, and electrous nickel immersion gold is a very good plating finish actually for a lot of things. However, it does cause more insertion loss, and this also will cause, due to the conductor effects, it also has an impact on the phase response. And this chart I'm showing here is showing extracted dielectric constant on the y-axis, and then frequency on the x-axis going from about 10 megahertz to 100 gigahertz, so very wide band. And the extracted decay on the y-axis, that actually comes from doing the microstrip differential phase length method, measuring a short length circuit and a long length circuit for phase angle, and then getting the affected dielectric constant using software to extract the decay at these different frequencies. Bottom line is, this is showing phase response, even though it's extracted to show dielectric constant. And this can give you an idea how much the phase response or the dielectric constant as perceived by the circuit can vary due to the ENIG varying in thickness. And this is a normal variation. This is what you would expect from circuit to circuit. So if you're making circuits in high volume manufacturing and you see variation from circuit to circuit, sometimes that's more problematic at lower frequency, where you have skin depth changing a little different than you do at higher frequency. So the final plate finish needs to be well thought out, and the effect on insertion loss and phase response are both can be very critical. So another idea, or another thing to think about for circuit fabrication for grounded coplanar waveguide specifically is, and this is used more again as feed lines at much higher frequencies, millimeter wave. There's a trapezoidal effect, and what I mean by that is, if you look at an actual circuit, do a cross section, a microsection, zoom in, what you find on an actual circuit is the conductors are not perfectly rectangular. They are more trapezoidal shaped, as I've shown on the bottom picture. The top picture is more ideal, and that's actually what most software will assume, unless the user tells the software to do something different. The trapezoidal shape can be, as I've depicted here, where the longer base is at the bottom of the conductor, but it can be flipped if a different process is used, and the trapezoidal shape could be inverted from what I'm showing, where the longer portion of the trapezoid would be on top or the air side. Regardless, the point here is, if the simulation's done with the top picture, where you have rectangular conductors and you have good coupling along the side walls, that's not the case when you actually build the circuit and you get more trapezoidal effect. And that trapezoidal effect will vary from batch to batch of circuits. So same design running in large volume with this trapezoidal shape changing can affect the insertion loss and the phase response. And the reason why is because you can see in the picture here, I kind of drew it a little exaggerated, where on the top picture you have fields between the ground signal ground on the top copper layer, and on the bottom picture, the trapezoidal effects actually causes the current density to shift down closer to the base of the material, and you have less fields in error. And with less fields in error, that means you have more fields in the substrate, and that means the effective decay will be higher, the phase angle will increase, the propagation speed will slow down, things like that. So if this is tightly coupled, it's a worst case scenario. Loosely coupled is less dramatic. But this trapezoidal shape will vary from batch to batch of circuits, or even within a batch of circuits, and that's a concern sometimes at millimeter wave for consistency of phase angle. Now, looking at this trapezoidal shape for a patch, and really the last topic I was talking about for grounded coplanar waveguide has to do with the feed line more than anything else. But the patch also can have some effect due to this trapezoidal shape, and here's kind of an extreme case where I'm showing the left corner or the left edge in a microstrip or a microsection view of a microstrip patch. And you can see as it's blown up to the bottom left there that it's got a really strong trapezoidal shape, or whatever you want to call that. And that means there's going to be pretty high current density out to that sharp peak there. And with that, increased fields, and these fields are going to be using that electrous nickel immersion gold. So that can be different than what the design was. If you did simulations on this, you probably would not do a simulation with a conductor looking like that. You'd probably think of it as either rectangular or maybe put in some trapezoidal shape. But this can make a little difference on the fields at that edge. And that is a radiating edge of the patch, excuse me, radiating edge of the patch. So that can be an important thing to consider. Now, this and also the previous slide with the trapezoidal effects, the best way to deal with this, I think, is to talk to your circuit fabricator, get a good understanding of what to expect for variation of this trapezoidal effect, and then try to simulate it in your software and account for it to make sure your circuit is not impacted by it. Now that's easier said than done when you really get into it. If you get into the field solving and really try to deal with these trapezoidal shapes, it's not quite as easy as you might think, or putting on some of the metals in the simulation to account for how the losses and the phase could react to different final plated finishes. It should be done, but it's not easily done. Anyway, moving on, got to speed up a little bit. I apologize, I'm taking more time than I thought, but here I'm showing a test vehicle that we put together. It's very similar to what's used at 77 gigahertz automotive radar, where it is a microstrip. It's a series fed patch design, and this is commonly used for millimeter wave radar. I'm not going to spend much more time on that. And give me a second. So, some of the things to think about for circuit fabrication as it relates to these millimeter wave antennas is the circuit definition and having 90-degree corners. Or actually not 90-degree corners when you build the circuit. It could be designed that way, and in reality, they're really not that way when you look at the final circuit. And that does have some effect on the performance as well as the trapezoidal shape. And under etching is another issue that comes up sometimes with some materials in the industry. Copper plating thickness, that is a normal variation of making circuits. One circuit to another of the same design will have differences in copper. And for a microstrip, that's not that big of a deal. It can make a difference in RF performance, but grounded coplanar waveguide or any coupled feature is going to be more impacted by the copper plating thickness variation. And then the final plated thickness, the final plated finish itself and the thickness also can cause more variation from what the design was intended. So for circuit definition, I'm showing a circuit that we designed, our test vehicle, simple microstrip series fed patch antenna, and you have the feed line coming in from the far left, and then you have a very narrow conductor, a wider conductor, narrow, wide, and this is kind of similar to stepped impedance structure that you might see in a low-pass filter. Same kind of concept, kind of, sort of. But anyway, this narrow line is very important for how this works, how one patch will affect another patch. And that narrow line needs to be controlled very well for etching. Now, I'm showing here that I designed this antenna as square corners between these narrow conductors and the large patches. And in reality, if you design it this way and simulate it this way, in reality what you get is a top view picture shown to the right there of that same pad, and you can see it's not 90 degrees. It's got some radius to it. And that's normal for circuit etching. It's not ever going to be a sharp corner with a few exceptions with exotic processes. But anyway, most processes is going to round that corner. And at lower frequencies, that really doesn't matter much. At higher frequencies, millimeter wave, that can make a difference. So when you're doing circuit simulations, again, it's good to talk to the circuit fabricator, ask them about this issue, and ask them what should be expected. And if you can do a simulation on this and understand how much that radius can vary, then that is desired. That can be difficult to do, though. Normally, from what I've seen in this particular design, I've seen this radius vary from 2 mils to 5 mils. Normally, if the fabricator is controlling this very carefully, you can minimize that variation, but it's still not going to be a sharp corner. And when you're at very high frequencies, that could affect the antenna performance. Here's a model that we did on a test structure based on what you've seen before, but a little bit more complex. And we put together this test vehicle to do some testing with it. And one test we did was talking to a fabricator, asking them what's the normal tolerance for etching, and they told us plus or minus 0.6 mil. And after talking to other fabricators, that can be controlled tighter than that. But for this example, what we did is we used our series fed patch antenna in modeling, and we varied a lot of the different geometries. And as we varied those geometries, we were looking for changes in antenna performance. And what we found was a conductor with changing plus or minus 0.6 mils will make a difference of the sitter frequency of plus or minus 0.55 gigahertz or plus or minus 550 megahertz or plus or minus 1.1 gigahertz. And that's a pretty good amount. Now, for our particular antenna, it did not affect our gain much, and it really depends on the antenna design. Sometimes the design is going to be more sensitive to this than other designs. Now, I just have a few minutes left. I'm going to go through this a little quicker. TCDK is thermal coefficient of dielectric constant. That's how much the dielectric constant will change with a change in temperature. Here is material testing at 10 gigahertz on several different materials. A worst case scenario I put in there just as a sanity check, I suppose. And that's the brown curve. That's FR4. It's not designed to be good for TCDK, and it's not. Some of the other materials in here are different materials with pretty good TCDK, and the RO3003G2, which is optimized for millimeter wave performance, actually has a TCDK of 35 parts per million per degree C, which is considered quite good, and that is the yellow curve in this chart. And the y-axis is normalized to the dielectric constant at room temperature, and 1.0 would be perfect, or in other words, 1.0 on the y-axis is 0 parts per million per degree C change for the TCDK, or in other words, the decay will not change at all with the change in temperature. So you can see that the yellow curve, 3003G2, is pretty well behaved, and then the RL3003 is just about ideal, and that's the dark blue curve. Now, when you do testing in circuit form, this is looking at microstrip differential phase length, so microstrip transmission lines. On the left is microstrips made on a 5 mil thick RL3003G2 materials, and I actually have 3 curves there, and each one of those curves were collected at different operating temperatures after the circuit and all the equipment came to a thermal equilibrium. So the first one is a blue curve, that's room temperature, about 25 degrees C. Next one's orange curve, 65 degrees C. And the last one, gray curve, 125 degrees C. So basically from 25 to 125 C, 100 degrees C change, how that impacted our circuits at 77 gigahertz built on the 5 mil RL3003G2 laminate was a change in dielectric constant of 0.01. And that's because it does have a pretty good, actually a real good TCDK. And then to the right is a material by a competitor that's trying to get into this industry with the millimeter wave radar. And their material tested the same way at 25 degrees C, 65 C, and 125 degrees C. You can see it responded with a greater change, about 3 times the difference actually, for change in dielectric constant as the circuit perceived it using our microstrip differential phase length method. Now, how that relates to an antenna is interesting because the TCDK will affect how the patch operates because it will change the decay as the temperature changes, but also the impedance matching network is going to change, and the impedance matching network is frequency dependent. And if the decay changes much in the impedance matching network, that could be maybe more problematic than the patch itself. So we did a test on this, and long story made short, the table on the bottom right is the summary of what we got out of this, again using our series-fed Microstrip Patch antenna test vehicles. We did this testing on 4 different materials, 3003G2, CLTE, MW, a competitor PPE-based material out of China, a competitor PPE-based material out of Japan, and the 2 far right columns are probably the interesting points. And this is collected at 77 gigahertz. This is looking at the S11 dip at different temperatures, and you can see the frequency shift between 25 degrees C to 125 degrees C. The column to the right, where it says frequency shift, we get about a 24 megahertz shift using RO3003G2, and that's equivalent to about a decay shift of 0.0002. And then the CLTE MW has also a good TCDK, and there we see about a 17 megahertz shift due to a 100 degrees C difference. And then you can see the PPE-based materials have quite a much bigger shift at 100 megahertz to 200 megahertz. Now, not all PPE materials respond this way, but a lot of the PPE materials I've seen on the market that I've tested do have poor TCDK, and they do respond like this. Now, this is our particular design, and in your design, it could be more sensitive to this or it may not be, but it's definitely something that you want to question and look at and try to do simulations to account for what could be happening due to these thermal cycles. So that's all I have for today, and I've gone through that pretty quick, I think, even though I don't have much time. Sorry, but I think we do have a few times for questions, and I'll leave you with a screenshot of our Technology Support Hub and invite you to become a member. There you can find calculators free to use and some free for download. Have a Raj mobile app with a lot of different calculators in there as well, technical papers, video library, and you can contact an engineer or technical resource in your area. And with that, I think we have a few minutes for questions.
Yeah, thank you, John. I'll give John a moment to catch his breath there, but thanks to both John Coonrod and John Eakins for a great presentation. That was a lot of good information. So let's take a look at some of the audience questions. And please remember, it's not too late. Don't be bashful. If you have a question, you can still submit it using the Q&A window. But let's get started. So the first one, what are some things that can be done to minimize feed line radiation for antennas operating at millimeter wave frequencies?
Yeah, that's really that's one of those typical questions I definitely hear a lot, and grounded coplanar waveguide is really a good way to go, to be honest. But the thing about grounded coplanar waveguide, as I've shown, the normal variations in building the circuit for the copper being plated thin or thick, that variation makes a difference for the coupling between the signal line and the grounded coplanar ground planes of both sides. But also the plated finish makes a difference, the trapezoidal effects, there's a bunch of things. But you can use grounded coplanar waveguide at millimeter wave. You just need to account for those things. And also, the key thing is use the least amount of coupling as possible, because the tighter the coupling, the more sensitive the grounded coplanar waveguide will be to these circuit fabrication issues. And also choose a final plated finish that is immersion tin, immersion silver. And the reason why is because it's so very thin that the normal thickness variation does not have much impact on the RF performance. And that's a few ways to go about it. There's actually several different ways to go about it, but that's probably the best way to go about having a feed line that will have the least amount of problems and radiation at millimeter wave.
Great, John. Thank you. You spent a bit of time talking about etching and kind of manufacturing. How much effect on RF performance can etching undercut of a patch resonator cause?
Yeah, that's a good one, because we've troubleshoot some of those issues, and it's really interesting because undercut, if you really want to get in the details, undercut's been around for years and years for most materials, but you just don't know it because it's usually just a very slight edge. And at lower frequencies with large patches, that little slight edge that's different than the rest of the circuit is not that big of a deal. But being that it's a radiating edge, then that is more of a concern. Now, at millimeter wave frequencies, when all these features are much smaller, that same amount of undercut that's minimal, it could be just less than half a mil or a tenth of a mil. At low frequencies, maybe not that big a deal. At high frequencies, it is noticeable. And that's something else that you want to work with your fabricator on and make sure that they understand the undercut issue and to minimize it as much as possible. Because what happens is you get some lift, you might say, at the edge of the conductor between that and the substrate, and now you got a little air gap in there. And the air gap will make a little difference on the fringing fields, and unfortunately, it can also entrap some chemistries and cause some other issues. So that's something you want to work with your fabricator. Our materials we understand very well and have gone through this before, and we know how to deal with that too. So talk to us or talk to your fabricator or both.
Great, thank you. The next one, it's well known that copper surface roughness will impact RF performance. How does that impact the feed line and radiating patches?
Yeah, I hate to give the answer, it depends, but it depends. So the feed line's a little different because really what you're getting is for the copper surface roughness, the feed line is going to see an average effect of this roughness. So going down the feed line, if it's an inch or 2 inches long or whatever, this roughness is not going to be perfect. It's going to vary. It's going to be mountains and valleys, and it's going to have some variation, but the transmission line is going to see that as kind of an average, you might say, along the length. But at the patch edge, where the fringing fields are, where radiation is important, that's a very concentrated area for the fields. And in that area, the roughness can have more impact. And my bigger concern would be copper with a lot of roughness also means that you might say that the copper dendrites or the nodules are buried deeper into the substrate. So when going through etching, they have to etch more aggressively to get all the copper nodules out, because if you don't, and you have a copper conductor with little nodules next to it, that's not good for RF performance. So the feed line sees something a little different than the patch does, just by the way the fields are using the structure. So feed line's kind of averaging effect of the roughness, and the feed line is a more immediate or direct response, you might say, just because it's using a very small area.
Great, thank you. So here's a question that came in pretty early in the presentation, and I think you might have touched on a number of these points, but it probably serves as a kind of a good summary as what might be our last question. But what about the conductor loss and insertion loss for strip line as a feed line for aperture coupled antennas compared to grounded coplanar waveguide and microstrip lines? Is strip line better compared to grounded coplanar waveguide and microstrip lines as a feed line? Any insight on this?
Yeah, that's a tough one actually, because that just comes down to a lot of trade-offs. But normally, well, gosh, that's a tough one, because I've seen a lot of different ways of going about this. And strip line's really good because you don't have any concerns with dispersion, radiation, and if it's designed right, you really don't have worries with spurious modes and all that kind of stuff. So that's good. So you can get a feed line and strip line that's basically getting the energy to where you want it to be very efficiently. The trick with strip line feed line is that you have to via up to the outside layer to get to the patches to radiate, and that transition a millimeter wave can be a real headache. At lower frequencies, it can be a headache too. But there's different ways to do that. It could be through a plated through via, it could be an aperture, it could be different ways, and that's something the designer really needs to go through and play around with the different tricks. Now, if a grounded coplanar waveguide is designed correctly and it's coupled just enough to get the performance needed, then that can actually be a good way to go. And I've seen several millimeter wave antennas using grounded coplanar waveguide as the feed line, but it does have to be well considered for the variations due to circuit fabrication, how it impacts it. And to compare strip line to grounded coplanar waveguide, I don't know if I really have a good answer, to be honest. They both have their pros and cons for the different things that you can get out of it. For grounded coplanar waveguide, you can actually get a little bit lower losses than you can strip line, depending on the design of grounded coplanar waveguide and the materials used inside the strip line. And that's just basically because the grounded coplanar waveguide has a benefit of having some fields in error, which is the lowest loss. But yeah, I don't have a real good direct answer. That's just kind of a mix of things.
No, well, that's great, John. Thank you. And unfortunately, I want to be mindful of everyone's time. So I think that's all the time we have for this webinar. So let me thank John Coonrod and John Ekus again for the presentation, and Rogers Corporation for sponsoring it. We did have a lot of audience questions, and we've captured all of them. So if we didn't get to your question, these gentlemen have kindly offered to get back to you with answers, so that's great. The webinar has been recorded, and it'll be available to watch in about an hour. You'll find it in the events section of the Microwave Journal website under the events tab. So please feel free to share it with any of your colleagues who may be interested. And let me close by saying thanks to everyone for joining us today. Keep an eye out for upcoming webinars and panel sessions, and I hope you all enjoy the rest of your day. Thank you.